Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, HetNets and Small Cells, presented by Anritsu. Our presenter today is Rick Fong, Strategic Business Development Manager at Anritsu. And at this time, I would like to hand the presentation over to Rick.
Thank you, Kyle. And hi, everyone, and thank you for joining this webinar. This is a new topic that we're presenting. Today's webinar is on heterogeneous network and small cells. And so this is an overview of technology and the standards, and we'll be going perfecting the industry right now, and then at the end we'll have a Q&A session where feel free to post questions and ask. So a little bit about myself and Anritsu. We are a global company of we manufacture test equipment for all industries, and the one that I'm focusing on today is on wireless tests and measurement, which is aimed mostly at LTE and cellular technology, but we also have products that support Wi-Fi, Bluetooth, and other type of technology, Ethernet, and so forth. I've been with the company about 3 years, and I've been in the industry about 20 years in wireless and telecom, and in different capacity working in technical sides, as well as marketing and product management side. But today's presentation is really a kind of high overview, a little bit about technology, a little bit about the market, what's driving the need for small cells, and facing the challenges faced by operators today of meeting capacity and coverage. So with that, I'd like to go ahead and start the presentation. So this is kind of an overview of what we'll be covering. Just an introduction to small cells and HetNet. Those terms you probably hear interchangeably, but they're quite interrelated, and I'll explain what each of those mean. Then I'll go a little bit into the details of what the benefits of small cells versus macro cells, and what's happening in the market today in terms of deployment of small cells. Then we'll talk about some of the challenges facing the deployment of small cells, and then some of the testing challenges in terms of user equipment as well as network, and wrap up with a summary of where the market is today and what we probably see happening in the market in the next 12 to 16, 18 months. So to start off, what's the driver? What's driving the market to consider small cell and HetNet? Mainly it's because of the growth, the explosive growth in mobile data. As we all seen, there's all kinds of report statistics, all pointing to the fact that mobile data is growing year over year, very, very quickly. And this is just one of many studies and statistics I put out. This one's published by Cisco, but saying that mobile data itself is tripling or even 5x over the next few years, and mostly it's driven by video. But not only that, is that the portion that is driven by video tends to actually go even higher. Right now, currently in about 65–70%. Previously, it's about 6%. So it's projected to actually reach even 8% of the total volume of mobile data. And the data itself is actually growing very quickly year over year. And secondarily is this number of devices that are connecting to all the mobile networks. There's some studies saying that for the next 5 years, really, the number of devices it's going to be 10 times as many devices we have today. So the volume of data, the number of connectivities that networks worldwide are going to be supporting is a huge number. But lastly, the most important point is that operators really looking to expand their network and increase coverage and capacity, really, because of the demand, but because they need a way to figure out how to deliver that data more cost effectively. Today, the cost of delivering 1 gigabyte of data is not coming down as quickly as what the users are really paying for it. So the ARPU for data is actually decreasing at a rate that's faster than any cost reduction can be had from increasing capacity using LTE Advanced, carrier aggregation. All those technology can reduce the cost of delivering the data, but it's not coming down as fast as the price the users are paying. So in a way, for the operator, they're kind of forced into a difficult position where the margin is actually squeezed down to zero effectively. And so they need to actually keep up with that trend. And small cells and HetNet is a way to do that. So let's go ahead and talk about what is a small cell, just so we have a common understanding what it is. and what HetNet is. So this is definition I just pulled from the small cell forum, but other places have similar definition. Basic small cells are like a microcell, but they're small in several aspects. It's small in terms of the radius of the coverage. That is, it covers a smaller area. It's small in terms of power output. As you can see at the bottom there in red, those are the typical type of small cells compared to a macro cell. And also the number of users. So typically a small cell, you can see there, it's support on the order of maybe 100 users, maybe 200 users. They consume much less power. They also transmit much lower power. So the power consumed is actually in the order of watts. And as such, it doesn't require any active cooling, any moving parts, any fans, which reduces the cost of the cell, the equipment itself, but also reduces the cost of maintaining the site and any facilities that are needed to support that cell. So if you think about a small cell, it's really kind of like a Wi-Fi access point that you may have at home. It's really just a passive equipment that's installed and operates about that same power and same coverage area. And lastly, small in terms of physical size. You think of a small cell nowadays, a lot of companies are building and marketing small cells. They're really on the order of fractional cubic foot, like a quarter to a half cubic foot, or 5 to 10 liters of volume. And if you think about that, that's the typical size of, say, a kitchen toaster, for example, if you can imagine. That's what a small cell would be in physical size. And that allows it to be easily installed in places almost anywhere. It doesn't need to go up on a tower. In fact, a lot of deployment will be at street level, and we'll talk about that and how that's used. So for comparison there, you see a table at the bottom. The macro cell today, I mean, of course, it can range from hundreds of meters to even dozens of kilometers in terms of radius. But typically, they're about 1 kilometer, the typical size. And then small cells are the 3 types you see listed below in red. We have outdoor microcell, which is similar to a macro cell, but smaller radius and smaller in terms of power. And picocell, which is smaller still and used in a different environment. And typically they're deployed in a enterprise environment. For example, if you think about a large campus or perhaps a university or a shopping center. Whereas macro cell more public spaces like a large transportation hub, like an airport or a train station. And then finally, femtocell, which is more like a Wi-Fi access point you have home, and those are typically could be installed and deployed by the end user, or could be installed by a network. But they serve a small number of users per cell and much lower power. So those are the types. That's what we mean when we say small cells in terms of coverage, power, and size. And next, we'll talk about HetNet, or Heterogeneous Network. So you hear that term quite a lot, and as related to small cells. And what it really means is that it's a topology of cells where you combine the macro cell working alongside with femtocells and picocells and microcells. So this is a picture I took from a Qualcomm presentation. I think it actually really well illustrates what that means. So on the left there you have let's look at the middle, the macro cell. So this is your typical cellular network that we have today, mounted on high up on towers with antennas, and then they're backhaul using fiber or gigabit Ethernet. And then on the right side there we have a macro cell. So these are lower power. They could be deployed by the operator, or they could be deployed by a third party, or even a third party system integrator or such. And typically they could be indoor, outdoor, closer to street level, because the size themselves, the cell size themselves are smaller. And on the left there you have femtocells and even Wi-Fi access point. So HetNet doesn't necessarily mean cellular technology. It could also include Wi-Fi and 3G and LTE alongside each other. So in this case, a femtocell would be deployed by the end user, and there could be many hundreds of thousands of them, or even millions of them in the network. Okay, next we'll talk about the benefits of small cells. So obviously, by increasing the number of cells, we can increase the capacity, barring issues with interference. and we'll talk about that, how interference can be managed and how that can be mitigated so that doesn't reduce the capacity overall of the network. But basically, when you add more cells to the network, obviously you would get more capacity. And in the case of LTE, that's especially true because LTE most deployment use factor of 1, meaning all the cells use all the frequencies that are allocated to it. So instead of allocating portion frequency to each cell, you actually allow all the cells to use all frequency. So if you think about adding, let's say, doubling number of cells by, let's say you have 100 macro cells and you add additional 100 micro cells or small cells to the network, that really increases capacity because each cell then have capacity X, and now since you have 2X number of cells, that would be double. So increasing capacity is the most important thing. Second, really factor for operators is really improving coverage. Micro cell work well on outdoor environment, but as people spend more time indoor and accessing the network and mobile data indoor, or in urban canyons where there are tall buildings, where the path there's a great path loss, there's actually a need to improve coverage, and putting more macro cells high up on buildings and towers does not necessarily achieve that goal. So small cells allow that to be the case. Small cells can be deployed indoor, they can be deployed at street level, they can be deployed in or even outdoor environment, but like a university campus. So you can really improve coverage in spots where there are holes of coverage from the larger macro network. So that's the second benefit. The third one is really reduce costs, and we'll on the next page we'll see some of the studies that are happening. But a lot of the industry now are looking at this as a way to reduce the costs on the order of 1/2 or even 1/3 or 1/4 compared to a macro cell deployment. So typically a macro cell would be on the order of hundreds of thousands of dollars for the equipment themselves, and maybe $1 million to operate and run the network over X number of years, say 5 to 8 years. And the small cells would be maybe $100,000 for the cell, or $50,000 to $100,000 for the hardware and the network, and the operating cost will be also a fraction of that. Third is reduced power consumption in the device themselves. So because, and this really relates to the coverage and the deployment model, because the cell sites are closer to the actual users, and because of the less path loss, there's less power that's required from the UE themselves to broadcast and transmit. So it improves battery life in the device themselves, but it also reduces power consumption in the network as well. And lastly is improving connectivity, and that's really measured by in terms of metrics of cell completion, call completion, and call retention. So that means firstly, the number of call attempts that are initiated, how many of those actually go through from landline and 3G and LTE. Users really come to expect a 99.5 or 99.9% completion rate. So I mean, anything more than a few calls out of the thousands not being able to complete, it's really seen as a network problem. So operators don't want to have to deal with that. And the second metric is really call retention. So how does the call stay up? How often does the call get dropped? And a similar type of KPI, really 99% or higher in terms of call retention rate. So you can't really drop more than, say, a few calls out of 1,000 to keep up with that kind of metric. And thirdly is really call delay. We have come to expect end-to-end delay from anywhere in the world to anywhere else in the world of a quarter second, or around that the range should be the maximum delay that we want to experience in a call. So backhaul and QoS have to be managed in order to achieve all those metrics to improve connectivity. So those are the benefits of small cells. And next we'll talk about one study, but there are many studies that have come up similar conclusion, and that is the cost of small cells is much lower than the macro cell or the larger cells. So in this case, this is one study sponsored by the Small Cell Forum, and it's looking at cost of ownership, total cost of ownership in terms of capex to deploy a cell, and also opex over 8 years. And it's a little bit confusing, but basically the chart is showing the cost per megabit of per second of data speed. So if you take a typical cell, let's say LTE cell of 150 megabits per second, what that translates to is a macro cell costing 780K for CapEx and OpEx over 8 years. Contrast that with a small cells using that scale, it would be less than about a third of that, 290K to deploy a cell as well as to operate and run it and maintain it over that same period. So this is one study, and it takes into account things like it's the same type of backhaul being used, same type of traffic loading, same type of environment, and deployment sometime about now, the late 2014, early 2015 timeframe. This is to demonstrate the cost difference between a small cell and macro cell. Next, I'd like to go over some of the market updates, but this is just a snapshot of what's happening in the market today in terms of small cell deployment. So SK Telecom in South Korea is really heading the charge on this. They were the first one to actually have a large-scale deployment of small cell into their macro cell network. And they've actually been doing this for about a year now. I think it started early last year in terms of adding macro cell. I think right now they have tens of thousands of microcells, maybe even 100,000 microcells by now in their network, so, mostly in the Seoul area, but also in outside of Seoul. And recently they have added EICIC, which is interference management technology. That's part of LTE Advanced. It's able to SK Telecom is able to use this in the network because we'll see later, interference is actually a big challenge for small cells because you have so many cells that are next to each other, so many cells that are overlapping, and so interference is a way to maintain that increasing capacity without mechanism like EICIC. Any benefit that you could get from deploying more cell would simply generate more interference, and so interference is really a key to deploying effective HetNet with small cells. Next is the recent announcement by Vodafone at the end of last year that they've signed an agreement with an advertising firm, JCDecaux, and this is actually a typical, I would say, very good example of how small cells could be deployed effectively. So JCDecaux, this advertising firm, owns a lot of what they call street furniture. That is outdoor billboard, bus stops, and signposts at street level, which have power, which have a lot of visibility, and Vodafone signs agreement with them to basically install small cells into those street furniture. So if you imagine people waiting at the bus stop would get cell coverage that is from a small cell extending maybe 100 meters from that cell site, and at the same time the cell could be using the power that's already available. It's really just a matter of providing backhaul and installing those cells, tens of thousands of those cells across a city, in order to provide this coverage. So I think that's really a good example of how small cell could be effectively deployed. In this agreement, actually, the advertising company is actually designing the housing, the outer housing of the unit, in order to blend in the small cells along with the surrounding. So that you won't see, huge white gray boxes with antennas sticking out. It will actually be covered up so that it will be basically unobtrusive. It will blend in with the environment. And lastly, it's a article actually provided by the Small Cell Forum, and the statistics a little bit old from a year ago, but basically it's like worldwide right now there's about 8 million small cells. Most of them are residential femto cells, so these are like access point that you would install in a home, but instead of Wi-Fi, they're actually LTE or LTE Advanced Wireless Technology, cellular technology. That's by far the largest number. However, there's also deployment in enterprise. You can see there's actually over 100,000 enterprise-based small cells, as well as 120,000 indoor or urban small cells. So these are deployment in, say, a company campus or a university campus, a kind of private public space. And indoor could be anything. It could be inside a coffee shop, a shopping center, a train station, airport. those are places where coverage is very difficult for macro cells, so it makes a good business case to deploy these small cells in those environments. And then lastly, there's also outdoor small cell deployment for rural and urban areas. So at about a year ago, there was actually 64 operators that have already completed trials and started commercial deployment of small cells using what we defined earlier as small cell compared to a macro cell. Okay, next I'd like to talk about some of the challenges for small cells. We talked about the benefits, but obviously nothing comes free. So there are challenges, and we'll go through some of the key ones right now. First and foremost is siting. So siting is really the selection and choosing of a site, and also gaining access to the site. That sounds simple enough, but really there are many facets to that. There are a lot of regulatory implications. Because now you're installing some equipment outside. It could be on lampposts, it could be at bus stops, it could be on street corners. Those actually have different regulatory requirements depending on what city you're deploying in. Of course, there's also federal requirements in terms of power output, because now you're really deploying equipment that is not on a cell tower hundreds of feet up in the air, but really at street level. And of course, it has to be unobtrusive, because a lot of cities, especially in Europe, they don't want any kind of outdoor furniture that would take away from the city, the beauty of the city itself. And of course, the unit has to be compact and lightweight, so it's easily hideable, if you will, and installable and replaceable quickly. So that's really one challenge. And even though it's two bullets, there could be whole discussions about that. But just keep in mind that selecting sites is a huge factor, and small cells tend to be much higher number in the network eventually than the number of macro cells. So, for example, a heterogeneous network could have 1,000 macro cells, but it could have tens of thousands or even 100,000 micro cells. So each of those cells have to be installed and sited and maintained. Next is providing power. We use the example of the advertising sign, so the power there is not so much issues, but you have to consider that the number of cells that have to be deployed at street level, running power to all of them is going to be a huge headache actually. And of course, all the cells do have to have some kind of battery backup in case of a power outage or accidental disconnecting of power to any of those locations. Third is backhaul. That is providing capacity to connect that back to the network. And there's really two models. One is capacity-driven and one's coverage-driven. So if you're deploying a small cell and you're deploying for capacity requirement, you really want to have the backhaul that can operate up to that cell's maximum throughput. So for example, if you have a cell that's capable of 150 megabits, you really want to provide enough backhaul to reach that speed. Whereas for coverage-driven, you're really just providing coverage. You're not really expecting to hit the peak traffic, but in that case, you can then back off a little bit in terms of requirements of the backhaul. And one thing to keep in mind about backhaul is that because there's so many cells and they're at street level where things can happen, digging a trench, plumbing, anything that's happen to cut the cable or your connection on the backhaul. So the network really needs to have a way to auto-configure or reconfigure itself quickly to maintain coverage and quality of service. And also at the same time, we keep in mind that because of small cell and their deployment, oftentimes the backhaul may not be totally owned by the operator themselves. It could be a lease line. It could be, for example, if it's in a large shopping complex, that backhaul could be Ethernet that's already installed in the building. And so therefore, the operator, even though they are not owning the complete network, they do have to maintain the network so that it can switch over, can reconfigure itself when cells drop out, when cells come back in. All that has to be done in real time. So that requires careful management of all the cells and taking into account that backhaul is not as reliable as on the macro cell. Next is interference. We talk a little bit about how interference could be a problem and how we can get around that. So interference, now we have considered interference between small cells because these will be deployed, say, 100 to 200 meters apart in a dense urban environment. And also interference with the macro cell. So it requires tight synchronization between the cells to make sure that, and we'll talk about how the different interference methodology can use that, but it requires tight interference in terms of timing and in terms of frequency to really reduce the interference between all the cells. And related to that interference is really some kind of advanced interference cancellation technique to ensure that any capacity gain by installing more cells is not lost to the fact that you're also creating more interference in that same environment. Okay, and mobility management. It's just really managing interference as devices or people move across the cell. For example, if you have a small cell deployed in the urban environment and someone drives through that street block, they could be on a macro cell, but then they enter in a small cell and then they quickly leave it within a few seconds. The mobility management has to know that you probably don't want to hand over to the small cell or micro cell for a few seconds and then hand back to a larger cell. So you have to be able to have some intelligence to tell which calls should be handed over between the larger macro cell and the small cells, and which calls should not be. And because if if handover happens too often, it could impact capacity. And if it doesn't happen often enough, it may be a call drop. Okay. And lastly, is a security concern. Security is always a concern for any kind of network, but particularly for small cell, because now the cells themselves are actually physically close to where the users are. They're deployed at street level, so there's actually physical security, how to secure the equipment. And then there's of course security in terms of the data backhaul, the data network, in terms of hacking and DOS attack and so forth. So those are challenges a lot of operators will have to think about and consider and overcome to deploy small cells. But it certainly small cells certainly have its benefit in terms of providing coverage and capacity. Okay. So next we'll talk about some of the technology that can be used to mitigate some of those challenges. First and foremost is the cell range expansion. This is a way to, it's really a cell selection algorithm that's deployed in the network, and then takes coordination between the device themselves and the network in terms of selecting which cell a device should camp on. So if you think about how a small cell, as we mentioned, is much higher power output compared to a micro cell. If a user is within the range of a micro cell, it should be connected to a micro cell. However, the micro cell has much higher broadcast power, so output power. So in most instances, it would actually see the micro cell as a cell that it should camp on. And so cell range expansion is a way, it's actually an algorithm that adds an offset to the receive power in order to basically force the UE, the device, to select the smaller cell, even though it has lower power. The reason you want to do that is because the smaller cell has less path loss, which contributes to saving power, battery power in the device, but it also improves uplink. Remember, the device is limited in terms of how much power it can put out in order to send data to the network. And if it has to boost its power in order to reach the larger macro cell, it's actually using more power than it should. Meanwhile, if there's a smaller micro cell nearby, it could connect to that. Now, even though the power is lower on that micro cell, it is actually better link, better connection, because it's using less energy, and also because it's closer. So micro cell and micro cell deployment, HetNet deployment, actually introduces this type of issue where you have a huge difference in terms of power between the larger cell and smaller cells. And cell range expansion is a way to manage the cell selection. It's really an algorithm that chooses the difference of the power based on, and it can be selected by the operator in terms of how many dBs difference to introduce in an algorithm. Next is some of the interference management techniques. So EICIC was introduced in release 8, and then EICIC and is in later release. And really, there are ways to coordinate cells so that they don't interfere with each other. ICIC is really a frequency domain interference. So basically, you take a frequency and you divide that up among the cells. So you could have half the frequency assigned to the larger cells and half the frequency assigned to the smaller cells. That's one example. But there's also a time domain interference. So by splitting up the frequency, you're really giving up half the capacity, right? You're not having to access the full spectrum or the full band of the frequency that operator purchased. So one way is actually to use all the frequency for all the cells, but assign time slots where each cell can use that frequency. So that's where you have time domain interference coordination coming into play, or with EICIC. That takes into account that not all the cells are broadcasting at the same time, and when they're not, the neighbor cells could be talking, or other cells that could be sending or receiving, and using that same frequency to transmit or receive information. Next is SON ANR, or self-optimizing network, automatic neighbor discovery. So this goes back to the fact that you have so many cells and so many users, and the RF environment is constantly changing, right? There's requirements to maximize the capacity and usage of the air interface, but since the air interface RF environment is constantly changing, you really need a way to adjust the network in terms of the cell radius, in terms of power, in terms of what cells are broadcasting what frequency and at what time. And so self-optimizing network is really a way for the network to adjust itself depending on needs. So for example, if you just think of, let's use a simple example of rush hour. At the end of a workday, everyone is leaving, say, a downtown area, and they get in a car and they tend to be mobile. So you probably want to shift off, put most of the users onto the macro cell network, because if you kept most of the users still on a smaller local microcell network, you would have so many handoffs that you have to process in the network, and that really just bogs down network. And the network is not going to be able to handle that. So the network has to learn to cope with that, and part of it is using intelligent algorithms to see what kind of patterns are in the network traffic, and also what happens when certain cells become unavailable. So for example, if a cell goes out of service, the network itself has to adjust and expand neighboring cell to cover that hole, that area that is no longer being covered previously. So that's one way to address that challenge. Next is by carrier aggregation. So carrier aggregation really is using different carrier frequencies and coordinating them so that the particular device could be receiving signal or talking to the network by different base stations, by different carriers frequencies. This is not particularly specific to a small cell, but carrier aggregation is a way to address the interference problem. And lastly is the coordinated multipoint. This is a way for the network to actually have multiple cells broadcasting to each device, and for the device to reach the network on the uplink. It takes coordination between the network and the device to assign frequencies. And if you think about it, one particular example that I'd like to use is if, let's say, a device is in an environment where it has access to a microcell, but the access is unreliable, meaning it drops in and out. So in that case, you could use the larger macrocell for the control channel. Control channel, as you know, has much higher robust channel quality. There's more error correction and robustness to the control channel. So that could be kept at a macro cell. Meanwhile, the micro cell could be used to deliver user plane data. And even though it's not as reliable, there's fluctuation in terms of quality of service. Still, the user can receive the data, because a lot of data is not necessarily so time sensitive, right? If you're downloading a web page, it doesn't have to be within the millisecond. It could have some fluctuation in terms of the coverage, but in this case, it could benefit by the added capacity, the increased coverage of delivering the content on the smaller cells, but still maintain connection to the larger macro cell for the control channel. So that's one way of splitting that up and gaining access to increased capacity. Lastly, we'll talk about some of the testing challenges. So for small cells and HetNet to really become effective, a cost-effective, economic, viable solution to increasing capacity, a lot of the devices and the network themselves have to be tested. And as I think you can see, deploying a HetNet, a heterogeneous network of combination of macrocell and microcell, is really quite different to deploying a network consisting mostly of macrocells, because the difference in power transmit level, and also the interference and the smaller cell size in terms of a handover, all those have to be considered in order to have a cost-effective, economically viable deployment for small cells. So some of the testing challenges that I see that need to be that we need to take in consideration when we introduce devices that supporting small cells, really interference management. That it requires the device to be able to listen in and monitor more neighbor cells in each area, collect that information, do all the measurements, interact with the network to send data and make intelligent decisions on when to do handoff, when to select one cell versus another, when to camp on one cell versus another. So that's actually requiring much more power, processing power in the device in order to do this. Another challenge is really quality of service, or quality of experience. Because of the introduction of a backhaul network that is maybe not be entirely owned by the operator, there is quality of service that needs to be adjusted and tested. What happens in the small cells? How does a UE cope with the fact that there's large fluctuation in terms of what can be delivered over the air, what can be sent over the backhaul, and how that cell selection process happen. Next is data throughput, so that's always a key, but in particular now, because we have different cells and could be much lower power and have much more fluctuation in terms of throughput, that's another area of testing. Carrier gauging, as we mentioned. And mobility and handover, this is particularly interesting, I think, for small cells. Since small cells, as I mentioned, is quite small, a few 100 meters or even less in terms of cell coverage, it works well for a non-station person. So if someone's sitting in a coffee shop, restaurant, it's fine. But if they go outside and walk about, that's still okay. But if they get in a car and start driving, the small cell coverage really is not suitable for this kind of environment. So the network actually has recognized that. The network has recognized the fact that someone is now moving at a certain speed or changing cells very quickly if you were to keep them on a small cell coverage. So the network has to make an intelligent decision to hand over to the macro cell so that that person doesn't, that device doesn't keep impacting the small cell in terms of taking up the resource to handle the mobility. It could be handing over from cell to cell to cell every 10 seconds or every 20 seconds. So mobility then becomes a intelligent decision that the network has to make to perform a handover. And lastly, and these are just topics, not particular order or priority. I just put them on here, but I think that they're interesting and should be considered when you're testing small cell deployment. Lastly is audio quality, and that relates really to QoS and quality of experience. I think devices, if you were to go in indoor environment where the macro cells have a lot of path loss, right? We all experience where the call drops, like when you step in the elevator, there's actually more garbled speech, there's that delay, and oftentimes there's even a call drop. So that has to be tested and considered if you're deploying a small cell, because there's more handoff between cells, so you don't want to introduce any kind of delay during the handoff. But there's also a need to maintain certain level of voice quality in order to preserve what users really come to expect in terms of cellular service. Okay, so in summary, I think small cells are really a cost-effective ways for operator to increase capacity and coverage of the network. And the keyword here is and. It's increasing coverage and capacity. Oftentimes you can increase one or the other, but not both, just simply by deploying more cells. But small cells allow the operator to do that because you can actually reach hard to cover area like underground or in building, but also increase capacity because you're actually using the same frequency and then adding more cells to the network. Siting and backhaul really the key issues for deploying small cells because there are more cells and also because they're deployed in an environment where it has to blend in and it has to have access to power and backhaul. But other factors actually also important to consider is network management. The number of cells that a operator would need to manage actually much larger. It could be 3-4 times compared to a simple macro cell network. As we mentioned, the cells have to be managed in a way in real time so that when cells drop, any coverage host introduced can be taken over by neighboring cells. QoS is always a issue there, of course. And then I just want to point to the fact all this really adds up to the reality that deploying small cells is quite different from deploying macro cells. Right? Macro cells have much larger power output and larger coverage, but with microcell there's more handoff you have to consider. There's algorithms that have to be tested in terms of handing over. If you hand over too often, there could be a ping pong effect. If you don't perform a handover often enough, then there's a call drop, and so it's a delicate balance between the two. So things like that have to be considered for small cells, especially compared to a macro cell deployment. And that leads really to the next conclusion, which is testing devices and network in a small cell is also different from testing a macro cell. Handover is one scenario. There's actually a work in 3GPP release 12 now that introduced a new UE category, a new device category that has intelligence to measure and make decisions about when to do handoff, how to report network measurements. So that has to be tested. Those are new technology, new methodology that's introduced by small cell that was not previously part of technology itself. And lastly is that Anritsu, we're a test equipment provider company, and today we have many solutions for LTE and LTE Advanced, and we'll continue to build on that technology and meet the needs of the market. And so lastly, I just want to show this. This is our product portfolio for LTE. I'll just quickly show this. So we have a portfolio of product covers from early development of chipset and devices on the left, you see there, to device integration and verification as the column highlighted in red there. And then we also have a product that tailored to carrier wireless network operators in terms of carrier acceptance of devices, especially for new technology. Devices have to be really tested well before they can be allowed onto the network. So we provide solutions for that. And lastly, we provide solution for manufacturing, for production and post-sales testing. So we have equipment that can actually do post-sale diagnostics as well as manufacturing process. So just in summary, we have a large portfolio of product to meet testing needs for LTE demand. And that really concludes the presentation part of this webinar.
All right, thanks, Rick.
I guess at this time I'd like to open up for questions.
Yeah, exactly. Rick, this is Kyle again. We've had a number of questions come in, so we'll jump right in. Just a note, for anyone that submitted a question, if we do not get it, Rick will get a copy of all of these questions. Anyways, the first question was about slide 11 when you were talking about audio quality. Were you referring to VoLTE or voice over IP?
Really VoLTE. And so VoLTE is really voice over IP on an LTE network managed by IMS signaling. Right. Voice over IP could be just end-to-end voice over IP, for example, a Skype call or FaceTime call. That's voice over IP. But when I talk about VoLTE quality, is really when I talk about audio quality, I'm really talking about VoLTE quality, and that means that provisioning a network and reserving resources in the network in terms of radio resources and also the backhaul and also the core network to carry that call end-to-end to ensure certain audio quality. So I guess the short answer is I was referring to a VoLTE quality, VoLTE audio quality. as opposed to just simple voice IP.
Great, thanks. Next question. What are some of the testing implications for device OEM and network operators to deploy HetNets in small cells?
Yeah, that's actually a very good question. The implication for device manufacturers, I touched upon that briefly, is that there's actually new technology, new algorithms introduced by LTE, by the 3GPP, to take advantage of this small cell. So there's new functionality that need to be tested. If you compare, say, a feature phone to a smartphone, and how much processing power that has today, that we see today in smartphone, I think that's similar magnitude increase in terms of going from a simple smartphone that operate in a macro cell network to a HetNet. And what I mean is that there are a lot of features introduced in release 11 and especially in release 12 geared towards supporting small cells, and all those features will need to be tested. For example, there are features to have the device monitor all the neighbor cells, make measurements, and report that back to the network, and even actually for the device themselves to make intelligent decision of when to request the handoff. That has to be done not only now for microcell, but also for microcell and femtocells, and that takes into account how much traffic the user is wanting to send or receive, how much interference is on one particular cell versus one that's, say, across the street at the Starbucks versus a bookstore. All that information has to be processed. So for device manufacturer introducing this type of technology, I think there's a lot of testing that needs to be considered before the devices can be allowed onto the network. And similarly for for the network operators, to really take advantage of the capacity increase with small cell and HetNet, that the network and the device themselves have been thoroughly tested, to make sure that they're all operating within parameters and within the expected behavior in terms of selecting cells, selecting handoff, and again, most importantly with interference mitigation. So those are kind of long answer, but those are the test areas I think need to be considered.
We had a couple questions about power consumption. Do you know what the typical power consumption of a small cell is in terms of kilowatts?
Oh, yeah, I think, let me go back to one slide. So I think this slide here, in terms of transmit power, it's really on the order of fractional watt to maybe 1 or 2 watts. So that's what the transmit power. And a lot of the microcell, or what in general we call small cells, that are coming to market today, the total power consumption is like 5 watts for the whole cell. So you think about something that is like a Wi-Fi access point. It has to consume very little power, first of all, because you don't want to generate too much heat, and it requires active cooling. It requires much more infrastructure to address that. And if you generate so much heat, you actually have to use fans with moving parts, so that reduces the lifetime of the equipment. So the goal really is to have the small cells, the equipment themselves, run on the order of a few watts, and that way it can be easy to deploy. They're lightweight. There's no moving parts, and ultimately they're also low cost. I hope that answers your question.
I think that seemed to hit it. Yeah, absolutely. So next question, could you provide a little more detail about 4G relay or wireless backhaul?
Yes. So backhaul, there's really two types of backhaul: wired and wireless, right? Wired backhaul is using fiber or gigabit Ethernet, and that's really the choice for operator that has that kind of infrastructure. So, for example, if you're in a city, it may already have fiber installed and it's available, but in some locations that may not be available. In that case, you would have to use the LTE network itself as a backhaul. So the macro cell then becomes the network that the smaller cell has to backhaul into. And so one possible scenario is that the small cells could have a directional antenna to reach a microcell that's on top of a building, and then the microcell itself would have another antenna to provide local coverage. at at the bus stop or the street level or the street corner. So that's one way to use wireless for backhaul. You can actually in LTE in the 3GPP standards, there's actually a facility to do that. You can actually use. Actually, let me go to this diagram. Yeah, if you see in this picture here, the blue arrow, the blue curve arrow in the middle of the picture, it says 4G relay backhaul. So that's you using LTE itself as a backhaul, and so the Metro Pico cell there really has no backhaul. In this case, you think about, let's say, deploying a small cell at a bus stop. There's no access to fiber or Ethernet. It's outdoor environment. It all has is electrical AC power, and it can run the cell. And so that way, in this scenario, the best way is to really backhaul into the larger network through the macro cell.
And next question coming in.
Oh, and I guess there's also option. Oh, sorry.
No, continue. I'm sorry.
There's a. Okay, yeah, sorry, there's a slight delay. I was going to say, LTE is not the only way to do wireless backhaul. You can actually use microwave as well, but it's not so cost effective. But that's why we choose 4G relay as a backhaul.
Great. Another question is there a reduced cost benefit to small cell if you're deploying a large number of sites?
Well, certainly, each cell themselves cost less than the macro cell. And they also tend to be portable too. So, for example, if for example there's an event and you quickly need to deploy coverage, let's say I don't know, it's just an ultimate case. Let's say there's an Olympic event and you want to provide coverage in, say, a few years ago in the Olympics in London. Deploying small cells is actually quite effective because you can do it at street level. A bit you have. Although you have more cells to deploy, you can actually deploy those cells very quickly. They're easy to deploy because they're lightweight, they're street level. You don't need a crane or you don't need to build a tower to put them up. And the cost themselves, of course, is lower for the equipment. And I think another benefit is that small cells, because you would have so many of them in each area, they can actually be powered on and powered off according to needs. So, for example, during business hours, more cells could be on in a downtown environment. And then after hours on the weekend, you can actually turn them off. You don't need to keep running them. The larger macro cell could provide coverage, and but you don't need the capacity that you would normally during the work week. So small cells has that advantage where you can actually turn off the cells if you're not using them, and then turn them back on if there's any traffic in that area, or if there's any increased traffic where the macro cell cannot handle it.
Do you think frequency spectrum will be allocated to small cells versus macro cells in some sort of standard?
It could be, but it's not really necessary because the small cells could operate at the same frequency as a macro cell. And in fact, that's how we really take advantage of the increased capacity. You use all the frequency spectrum, all the frequency band that operator has, and use them for both the macro and the micro. You could split them up, and that's one way really to reduce the interference. But depending on what the goal is, you might be better served, an operator might be better served to actually use all the frequencies. So I don't see a need to actually allocate certain frequency to microcell versus microcell, except the fact that microcell, because they're much lower power, they do have the ability to run or use unlicensed band. So, for example, one model is that the macrocell use licensed band, and the femto cells could use unlicensed band. And so you've heard of things like LTEU, unlicensed LTE, which really use the same band that Wi-Fi uses in the 5.4 gigahertz, in conjunction with the licensed band that the operator has. So that's a way to provide coverage indoor by using unlicensed band that's available or allowable to be used, and use that in conjunction with a macro cell. And that is one scenario where you can use the example I used earlier, where control channel stays on a macro cell and the user plane traffic goes to a macro cell. So that's one way to do that. But I think to answer the question, do we really need to have separate band license for micro cell versus macro cell? I would say not necessarily. If the frequency is available, it's actually better to use it all for all the cells.
Another question. So we've been hearing a lot about CRAN and VRAN in the industry lately. Would you consider that an evolution of small cells?
I'm sorry, can you repeat the first part?
We've just in the industry in general, we've been hearing a lot about CRAN and VRAN lately. Would you consider those an evolution of small cells? As
Actually, I'm not so familiar with the two terms. Yeah.
okay,
So I will have to take that as a question I can respond to later.
okay. So early in the presentation, you referred to backhaul. Would you describe that as how would you describe a self reconfigure in a network in terms of backhaul?
Uh, okay. Yeah. So backhaul, and that goes back to the fact that backhaul is not necessarily owned, managed, or operated by the network operator. So oftentimes, if you take the example on this picture on the left there, it's a femtocell that could be deployed indoors. So for example, I could be I could go to my operator. I say I want better coverage, and they say, well, we don't have the, you have the option of actually installing a femtocell in your home. So what the femtocell does is actually use my um, internet access in order to backhaul into their network. And in that case, the backhaul is not owned and controlled by the operator, but the operator still has the obligation to provide a certain level of service. For example, if I make a call on my phone but connects to my femtocell, it still has to be able to support voice quality of a certain extent. And so that means that the network itself has to be able to make intelligent decisions in terms of what happens if I start to lose capacity in my backhaul. My calls then should hand over to the macro cell. But in terms of the backhaul management, there's let's take an example like a outdoor environment or a public space environment where there are many macro cells. Some macro cells could be highly loaded, a lot of traffic on there. It could become available because there's a cable cut. In that case, all the neighboring cells would have to be adjusted, and in order to provide that coverage. And of course, the backhaul itself has to be monitored to see that capacity is available to increase coverage in that area. It's think about it as an ever-changing environment, and then you really have to monitor it. And so if we plan a network ahead of time and provision it, it probably won't be able to respond so quickly in terms of when there's outage. But if you have automatic detection of network fluctuations, network coverage drops, you can quickly respond to that, and the network has, of course, can be made to make intelligent decisions of how to fill in those holes, how to provide coverage to those areas.
All
I
right.
think that's what the question was asking.
Yeah, I think you hit it.
Okay.
So we have time for just one more question. Earlier, you talked about Release 12. Can you talk about some of the features with that would support HetNet and small cells?
Yeah, sure. So Release 12, I believe it's to be functionally frozen, I think in March, so fairly soon. And there has been a lot of work items in 3GPP to address many different areas. There's areas to address eMBMS broadcasts, but one of them was actually to address HetNet and small cells. So I think some of the work that's going on right now for small cell really focuses on the interference mitigation. One is what I talked about earlier, is cells can actually be turned on and off. So say after hours, it's better to actually turn off the small cells because there's more mobile traffic, in vehicles. So therefore, more traffic should be handed on them to a macro cell. There's actually procedures and algorithms to define to help devices detect and hand over to small cells. So there's ways for the device to actually discover if there's more cells in the area and when they should be handing off to those small cells or handing back to larger cells. There's actually work going on to define those kind of algorithm procedures. Another one is what they call dual connectivity, and this is where the device, as I mentioned, is using the macro cell for control plane traffic and using the local smaller cells for the user traffic. That's actually, I think, a very interesting way of increasing capacity. Another way is I think I briefly mentioned that. That's the UE enhancement. So there's enhancements to UE. There's actually a new device category defined, that has the capability to perform what's called network-assisted interference cancellation suppression. So the network can actually and the device can actually work together to see where there's interference and select different resources, different frequency or different channel or different time slot to reduce the interference between devices or between cells, so that it actually increases the throughput by reducing the interference. There's there's also well, yeah, and actually related to that, there's actually interface. The cells are using the X2 interface between eNodeBs in order to coordinate that interference. So there's actually a lot of work on the device side and also on the network side to manage this interference. And I mean, there's actually even a new UE category defined that has a capability. So I think that's actually a very positive step in the release 12.
That's about all the time we have for today's webinar, HetNet and Small Cells, presented by Anritsu. Again, I want to thank everyone for attending, and I want to thank our presenter today, Rick Fung, Strategic Business Development Manager at Anritsu. Thank you, Rick.
Thank you. Thank you very much.